Okay, proof, set theory, and logic, Wednesday. Look at us. If you've been following along in the schedule, you'll notice that we are nearly one entire week ahead, which is pretty cool. It's great. I didn't expect us to get through some of this as quickly as we did, so I am happy that we did. Today, we're going to talk about one of everyone's favorite topics, induction. So I think I asked last time, how many people have seen induction before? A lot of people. Okay, well maybe this will be easy then. If not, don't worry. I won't go too horribly fast through it, but we're in section 2.4, mathematical induction. A side note, I don't know why everyone calls it mathematical induction. Kind of like, you know, why prepend the mathematical part there? It's not like I'm getting it confused with some other kind of induction. It's not like I say, like, we're going to be learning about induction, and people go like, oh, like when like heat transfers through like a pan or something, like on your stove, or, you know, I don't know. But for some reason, most textbooks seem to call it mathematical induction. They always like to add that on there. The idea of it is not too crazy. So here is a theorem, which I will not prove to you at the moment, but this is the gist of it. This is called the principle of mathematical induction. And in fact, I'm just going to call it the principle of induction, because why prepend the mathematical there? So here's the idea. Let P of n be a statement about the natural numbers, or I'll say about the natural number n. So if P of 1 is true and P of n, or even P of k to be clear, P of k implies P of k plus 1, then P of n is true. Maybe I should be extremely clear right here. I will say P of n is true for every natural number n, but if this is true for every k, then P of n is true for every natural number n. That is, it is a statement about predicates on the naturals. And really, we don't actually need it to be a statement about predicates on the naturals. It's just phrased that way in your textbook. It can be said much more generally. There's nothing so special about the naturals other than the fact that they are nicely ordered. Effectively, you can do something very similar with other ordered sets, provided the ordering is sufficiently nice. Basically, it says, hey, if you can do it for one thing, and if having one thing gives you the next thing, then you can do it for everything after the first thing. Does that seem reasonable? Yeah? Okay. You can imagine, for instance, like a double-sided version of this for statements about the integers, where you say, like, if you can get one thing, and P of k implies P of k plus 1, and P of k implies P of k minus 1, then you've got it for all the integers or something, you know? There are many different variations of mathematical induction that you can do. All of them boil down to having the same fundamental components, which is that you can think of it like a ladder, right? You have to somehow be able to say that you can get on the ladder, and then somehow be able to say that being on one step of the ladder lets you climb to the next one. Does that make some sense? If you can get on the ladder, and you can climb from one step to the next, then you can climb to any step on the ladder, right? That's mathematical induction in a nutshell. Not too crazy. So every proof involving mathematical induction, just as like a kind of customary good form sort of thing to do, has basically the same structure. Here's the idea of it. Every proof via induction has the following form. I would say step 0, sort of, say you are using induction. Say something like, we proceed by induction. 1, establish the base case, that is, get like p of 1 or p of 0 or whatever one you're starting with. Show that you can climb onto the ladder. Then 2, assume p of k and show p of k plus 1. That is, assume p of k is true and show that this does indeed imply that p of k plus 1 is true. And then finally, usually, people say, that it's nice to at least clearly conclude that via induction, the statement is true. Let's do an example. Let's get used to this. You'll see many, many, many different cases of induction throughout your mathematical career. It is an extremely common proof technique, and I think people like it so much because it has such a good structure. It is such a convenient way to break down something otherwise difficult into little manageable bite-sized pieces. So let's try this. Let's prove the following theorem. Here's the theorem. For each natural number n, the statement is that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. You've perhaps seen this before. This is a moderately well-known result. There's a, well, I can't remember if it was Gauss or Euler or something. One of the two. I think it was probably Gauss? Yeah. I don't know. One of those famous ones, right? There's some sort of anecdote about, they're in grade school and their teacher was frustrated with all the kids or something like that and was like, add up all the numbers 1 to 100, okay? That'll keep you busy for a while. And supposedly he figured out a great trick to do it and came up with this formula, on the spot as a little kid or something. I don't know if I buy it, but that anecdote, I've heard it multiple times from multiple people. Perhaps it's true. I don't know. Good story nonetheless, right? Definitely something Mom would be proud of. So let's do it. Let's try it. Let's see if we are as smart as a young Gauss or Euler in this potentially fictional story. Let's see. So what would you do first? Well, let's follow the structure. State that we're using induction, yes. We proceed by induction. And then break it into pieces. Our base case. So what would be the base case? Yeah. Let n be equal to 1. Then the sum from I equals 1 to 1 of I, well, this is just 1. And would you agree that 1 is indeed equal to 1 times 1 plus 1 over 2? Okay. So the result holds for n equals 1. That is, we say, clearly specify what our base case is. It's the case where n is equal to 1. And I've forgotten to draw my serifs on this one. I often forget to draw serifs on 1s. I don't normally draw serifs on 1s, but I've tried to convince myself to do it over the years, and not hard to do consistently. Okay, so clearly state what your base case is. Show that your desired statement is true for that base case, and then clearly state that you have shown that, right? Okay, so this fact, this thing we're trying to show, we have indeed shown is true for one value of n, specifically the value n equals 1. Now we carry out the inductive step. So in the inductive step, here's how we do it. We want to show that p of k implies p of k plus 1. Now, when is an implication false? An implication is false if
P of k is true and P of k plus 1 is false.
exactly. This implication specifically would be true if p of k plus 1 was false while p of k was true. So we want to show that is not the case. We want to show that this implication is true. So we must show that if p of k is true, so too must then be p of k plus 1. So we'll start by assuming that p of k is true. So assume the result holds for k, i.e., we are assuming that the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. We show this implies the result holds for k plus 1 as well. I.e., I guess if I want to be entirely correct, I should put a semicolon after that, but I think that looks confusingly like a J on the board. I.e., we want to show that the sum from I equals 1 to k plus 1 of I is equal to, well, exactly the same thing, but with our k's replaced by k plus 1s. So there's my annoying way of writing it, very clearly showing that I've just replaced my n's here by k plus 1s. You could do some additional simplification, right? This is k plus 1 times k plus 2. But I'm just trying to be very clear there that I've replaced my n's with k plus 1s. Okay, so how would you go about showing this? The inductive step is usually the part of an inductive proof that is actually difficult at all, right? The rest of it is very straightforward and formulaic. The part with the inductive step is usually where all the magic happens, I guess, right? That's where all the tricky business goes on. So how will we do this? Well, the thing to do is use the information that we actually have available to us. What do we have available to us? Our assumption that the statement is true for k. So we will go through and use that fact to show that it also holds for k plus 1. So let's go through and do it. Okay. Computing, we have the following. So let's start with part of what we want to show. So we'll start with the sum from I equals 1 to k plus 1 of I. And we'll say, hey, you ever thought about how this is just the sum from I equals 1 to k of I plus, well, the last term of the sum, which is k plus 1, right? What would we do next?
Rewrite the sum from
I equals 1 to k of I as k times k plus 1 over 2. Do you agree with this? Nice. This is looking good so far. Okay. So now I will find a common denominator, k times k plus 1 over 2 plus 2k plus 1 over 2. Putting it all together, I have k times k plus 1 plus 2 times k plus 1. If I factor by grouping, I have k plus 2 times k plus 1 over 2. Or if you prefer, I could write this in the other order, which I will do so on the next line. he'll write this as k plus 1 times k plus 1 plus 1 over 2. Does that make sense? Hopefully it does. Or maybe not. Some people are saying, Bryce, I don't know about this one. You're saying, I'm not buying it. What do we got? Steps people are feeling weird about. I'm imagining that this step right here people are okay about, since I just flipped the order of the multiplication and wrote 2 as 1 plus 1. This step's probably fine. I multiplied the top and the bottom by 2. Is it this step up here?
Yeah.
Yeah? Okay. Some people are saying yeah to that one. The whole gist of it is that the summation notation here is saying starting from I equal to this value and incrementing by 1 until you get to the top value, add all the terms up. So if I increment by 1 until the second to last value, and then add the last value, it's the same way. Writing it more precisely over here, I guess if I have the sum from I equals, let's say a to b of some function f of I, then this is just equal to f of a plus f of a plus 1 plus da 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 all the way down through f of b minus 1 plus f of b. Yeah? Agree with that? Okay. So would you agree that I can do a little bit of grouping right here and write it like this with some parentheses? And then go, hey, look, this is the sum from I equals a to b minus 1 of f of I. And then afterwards, I can add on f of b. Get what I'm saying? If I'm taking 1 plus 2 plus 3, right, the sum of the numbers 1 through 3, I could write that equivalently as the sum of the numbers 1 through 2, and then add 3 at the end of that. Right? Cool. Okay, so that's the whole gist of what's going on in this first step. If you're feeling good about this first step, then all that happens in the second step is I replace the sum from I equals 1 to k of I with what I have assumed it is equal to. I think this is maybe the place where people get a little weirded out by induction, if they get weirded out by it. They say, hey, how come I can assume that's true? And the answer is that you can assume anything is true if you want. It doesn't make it true, right? We are not necessarily saying that it is true that the sum from I equals 1 to k of k times, or from I equals 1 to k of I is indeed equal to k times k plus 1 over 2. We're just saying, suppose it is, then if we suppose that, we also get that the sum from I equals 1 to k plus 1 of I is equal to, well, k plus 1 times k plus 1 plus 1 over 2. The same statement with k replaced by k plus 1. It does not actually have to be the case that it is true. That is, we still need our base case to start with. We have to have it be true for one case to get a full-on induction proof. Yes?
You simplify the second part. Sorry.
Right on. So someone asked, how did we simplify the second part? Which part, like over here?
Like the one directly under your finger, like not to get to the k plus 2. To get to this next one.
Oh, okay, here. There's maybe like I can write like the kind of missing step in here. Here. This, I just put everything on one fraction, so I have k times k plus 1 plus 2 times k plus 1 all over 2. And I say, look, I can pull a k plus 1 out of both of those terms and rewrite this as k plus 1, since it's multiplying both of those things, times k plus 2. Do you see what I'm saying? Cool. Right on. Algebra! The eternal stumbling block of every mathematician since the dawn of time. Yes. So we write that as k plus 1 over 2. And then, to finish off here, we would say something along the lines of, well, most people would just perhaps leave it like this. But if you want to be very, very clear, you would say something along the lines of, so the sum from I equals 1 to k of I equals k times k plus 1 over 2 implies that the sum from I equals 1 to k plus 1 of I is equal to k plus 1 times k plus 1 plus 1 over 2. Finally, we can conclude our conclusion step. If you want to be very clear, you get your base case, you do your inductive step, and then you conclude, and you say, by the principle of mathematical induction, yet again, why prepend mathematical? I don't know. A common thing. The sum from I equals 1 to n of I is indeed equal to n times n plus 1 over 2 for all natural numbers n. That is, it's true for all n greater than or equal to 1. We established the base case of n equal to 1, and we showed that having this statement implies the next statement. That is, having the statement be true for some k implies that it's true for k plus 1 as well. So since we were able to start with the statement at 1, this fact tells us that we get the statement at 2. And now that we have the statement at 2, this fact yet again tells us we get the statement at 3, and so on. Does that make sense? You can think of the induction step as like a little device where you put in, it's true here, you get back, it's true at the next one. And so as long as you have something you can put into there, right, a case where it is true, then you get all of the ones after that by just repeatedly applying this device to the result. Does that kind of make some sense? Okay. Perhaps it would make even more sense if we explicitly labeled all of these as propositions P of n. So to be mad clear about that, let's go and see if we can do it. So here, this n equals 1 case, we're establishing P of 1. That is, if this statement right here is P of n, and what we're trying to show is that for all n P of n, right, we want to show this whole statement here, the theorem, is all n P of n, where our domain is the naturals. Here's what we'll do. We show P of 1 is true. And then in the inductive step, we show, and I will just go back over to the other board now, we show that P of k implies P of k plus 1. And then in our conclusion, we say, look, I've got P of 1, and using my inductive step, this implies P of 2, and using my inductive step, this implies P of 3, and so on forever and ever and ever. And so we can say, hey, look, for all n, P of n, just like we wanted to. Does that make some sense? Induction. Neat. All right. Induction. So let's do another example. You guys try this one. Let's see. Let's prove the following. Here, I'll jump back a board. Let's prove the following theorem. I won't even have to erase most of this since the structure is relatively similar. Let's prove that for all non-negative integers n cubed plus 2n is divisible by 3. A fact that perhaps you would not have guessed first looking at it, but one that you may otherwise struggle to prove without induction. So, give it a shot. I will show you how little of this I have to erase. We will fill in the blanks together. I see people writing and writing. Good. Keep going. I will slowly start to put pieces up there, so if you get stuck on one, you'll be able to keep going. Please do keep trying. Okay, so I have written for some time here. I believe people are hopefully approaching the step where perhaps everyone's getting confused. Let's start on the basic parts of it. So to show that n cubed plus 2n is divisible by 3 for all non-negative integers n, we proceed by induction. First part, base case. let n be equal to 0. This is the smallest non-negative integer, right? Any integer smaller than that would be negative, yeah? So start with your smallest case and show that it's true. Oftentimes this is great and very easy because the smallest case is the easiest one, yeah? So if n is 0, then 0 cubed plus 2 times 0, well, that's equal to 0. And would you agree that 0 is certainly equal to 3 times 0? Yes, so it is divisible by 3. Okay, so the result holds for n equals 0. Now we proceed to our inductive step. In our inductive step, we assume that the result holds for some value k, i.e., let's assume that k cubed plus 2k is divisible by 3, right? Another way of writing this, if you wanted, would be something like this. You could say k squared plus 2k equals 3t for some t, some integer t. You agree with that? So that's what it means to be divisible by 3. It means you have 3 as a factor, yeah? Okay, we show that this implies the result holds for k plus 1, i.e. we show that k plus 1 cubed plus 2 times k plus 1 is also divisible by 3, yeah? Now the reason I didn't initially write this as k cubed plus 2k equals 3t for some integer t is that if you did this, I think perhaps some people may get confused and accidentally believe that this means that k plus 1 cubed plus 2k plus 1 would be equal to 3 times t plus 1. This need not be the case. We're only saying that it's divisible by 3, not that it is 3 times 1 more of whatever the other thing was when divided by 3, right? It's a different statement. Do you get what I'm saying? Just they both have to be divisible by 3. They don't have to have subsequent successive remainders after division by 3. So it's easy to accidentally add on some additional statement that you are actually not trying to prove that may be false if you're not a little careful. The only thing we're incrementing by 1 is k. Yeah? Okay. So to do this, we're going to go back and do our computation now. Switch the camera there. Okay. So computing, well, we just have to start with what we got. Let's start with k plus 1 cubed plus 2 times k plus 1, and let's show that the result is divisible by 3. We'll have to use our inductive hypothesis at some point. So we'll say k plus 1 cubed plus 2 times k plus 1, and I'll just write this out in its gory details. This is k plus 1 times k squared plus 2k plus 1, and then 2 times k plus 1 is 2k plus 2. Okay, now I go through and I multiply my k through everything, a little bit of algebra. K cubed plus 2k squared plus k. Now I do the 1 through everything, and I get k squared plus 2k plus 1, and then I still have my 2k plus 2 hanging around. Now I'm going to group everything together. The way that I'm going to do this is perhaps initially going to look a little confusing because you might say, why did I not put all of the terms together? And the reason for it is that I want to use my inductive hypothesis, which is that k cubed plus 2k is divisible by 3. So I will even highlight that. I have a k cubed and a 2k right there. I'm going to not bring those in with everything else. Everything else, notice, is divisible by 3. So I have k cubed plus 2k, and I have 3 times k squared plus 3k plus 3. Feeling okay about this? Or maybe not? What's the mood in the room? Good? Okay. It's like a thumb most of the way up. Yeah, kind of. Okay, reasonable. I can appreciate that. Okay. And so now I'll say, look, this is 3t for some t, and this is 3 times k squared plus 3k plus, oh, I didn't pull out my 3's here, oops, plus 1. Okay, sorry. 3 times k squared plus k plus 1. Sorry, I should have pulled my 3's out from every term in there. Oops, algebra can get us all. The idea was the same. Okay, so 3 times k squared plus k plus 1. And look, if I pull everything together, wouldn't you know it, I get 3 times t plus k squared plus k plus 1. Hey, is that an integer times 3? Yes. So k cubed plus 2k is divisible by 3 implies that k plus 1 cubed plus 2 times k plus 1 is divisible by 3. Our conclusion then becomes, by the principle of mathematical induction, n cubed plus 2n is divisible by 3 for all non-negative integers n. So we showed it holds for one case. That's the case of n equals 0. We said, all right, that's pretty good. Now let's show that having it for k implies it is true for k plus 1. That's the inductive step, our device that says, here's your result at one value, you get it at the next. And then we just repeatedly apply this to that one case that we showed, and we get it for everything doing this. That is, we have our ladder, and we said that if you're on one step, you can get to the next. And we said, you can get here, and you can go up. So you can go anywhere, right? You can get on the ladder, and you can go up the ladder, you can climb the whole dang thing. That's it. That's mathematical induction in a nutshell. What do you think? We said that a lot today. Who knows? Okay, cool. So let's do another example. Let's try it. This is definitely the place where people get the most tripped up in this section. I don't think most people are too confused about the idea of providing a counterexample like we talked about last time. We do that sort of stuff all the time. However, unlike many of the other things we've recently talked about, where I go, look, you've seen this in, like a TV show. You've done this in regular old life, right? I imagine that you probably have not done induction in a regular conversation with somebody. Perhaps you have. Occasionally it might pop up, but it is certainly a far less common rhetorical tool than, for instance, a counterexample. Yeah? Okay. Try this one. See if we can do this in kind of quick, short form. So prove the following theorem. Theorem 9 to the n minus 1 is divisible by 8 for all non-negative integers n. Try it. Let's see. And feel free, if you want, to be slightly less structured than the step 1, step 2, step 3. You can even write it, in like a more paragraphy form if you want. You can also write it in the structured way if you prefer. Yes?
I'm kind of confused because like I had always heard like you can't use 0 in the base case.
Oh, okay, so someone just said they're confused because they're saying, I've always heard you can't use 0 in a base case. I totally see where you're coming from. Indeed, if you go back to where we originally started, we indeed did state this about natural numbers, which under, I guess, the convention we're using here, though some people vary on this, and whatever you prefer, that we're starting with the numbers that are greater than 0, the integers greater than 0, right? This is a statement for them. Okay, fine. You can always do a conversion here. If you would like to start with the base case of n equals 1, then we could change this statement by replacing n with n plus 1. Or sorry, n plus, wait, let me make sure. If you would like to start with 1 instead of 0, then we would just replace n with n plus 1 to move it forward 1, yeah? Effectively, the point is that the important thing is not that this is numbers, like positive counting numbers that are greater than 0. The point is that they are all nicely ordered. One comes after the next and so on, right? So you could start with a base case of, say, like -7 as your base case, and then show that having it true for k implies it's true for k plus 1, and then you would have proved it for all integers greater than or equal to -7, right? So whatever you use for your base case, that's the smallest one you show it for. And then your inductive step shows it for all the rest, all the ones larger than that. Does that make sense? You could also do like a backwards form of it, where you start with your base case and then you show p of k implies p of k minus 1. You could go down if you prefer to do that. But the whole point of it effectively is just that you have a starting place, and having 1 implies the next, but implicitly in that what we're using is the fact that there is a next one, like a unique next, right? That the naturals are a big old chain, right, with one link after the other. So you can indeed use things other than 0 for the base case. If you prefer to always use 0, you can adjust your statement so that the 0 statement is the same as, say, or if you want to use 1 as your base case, you can adjust things so that like the 0 statement would instead be equivalent to the 1 statement for your newly adjusted 1. Does that make sense? Okay, yeah, great question. Right on. So for the proof here, let's do it together. Okay, let's prove the following, that 9 to the n minus 1 is divisible by 8 for all negative integers n. Let's try it. So we'll proceed by induction. For the base case, let's let n equal 0. Then, what have I done here? Maybe I should say all non-negative integers? Wait a second, let me think about this. Because then it's minus...
9 to the 0 minus 1 should be...
Oh gosh, what have I done? Yes, sorry, I have started with 1. I see why people were confused about that. Okay, because this is 1 minus 1, which is equal to 0, which is certainly equal to 8 times 0. And the result holds for n equals 0. I did n equals 1 right there, not n equals 0. Though if you did n equals 1, then you would just write what I said before. Oops, sorry. Thanks, guys. I appreciate that. My apologies. Okay, so the result holds for n equals 0. Now let's do the inductive step. For the inductive step, we'll start by assuming that 9 to the k minus 1 is equal to 8t for some integer t. That is, we'll assume that our statement is true for some value k. Yeah? We say for k, whatever it is, I don't know, we're saying it's true. That is, we're saying 9 to the k minus 1 is divisible by 8, so it's equal to 8 times some other integer. Yeah? 8 is a factor of it. Okay, we show that 9 to the k plus 1 minus 1 is divisible by 8 as well. That's what we'll do. We'll show that having it true for k implies it's true for the k plus 1 case as well. Okay, to do so, let's observe that 9 to the k plus 1 minus 1 is equal to, well, what did you do? Someone show me. What do you got? Did anyone get it? No? Let's think about it together. So somehow, what do we have to use? We have that 9 to the k minus 1 is equal to 8t for some integer t. Yeah? Okay. So 9 to the k is equal to 8t plus 1, right? Do you agree with that? All right, so here's what I'm going to do. I'm going to say, look, I got 9 to the k plus 1 minus 1. Would you agree that's 9 times 9 to the k minus 1? Yeah? So this is 9 times 8t plus 1 minus 1. That is, this is 9 times 8, I'll write it this way. I'll write it as 9 times 8t plus 9 minus 1. Would you agree that this is the same as 8 times 9t plus 8? Would you? I just flipped the order of multiplication right there. Multiply the 8 first instead of, or the 9 first instead of the 8, right? Okay. And I said 9 minus 1 is 8. And hey, if I factor it up, I have 8 times 9t plus 1. Well, that's certainly something divisible by 8. Yeah? Oh, okay. So, whenever 9 to the k, not plus 1, minus 1, is divisible by 8, so too is 9 to the k plus 1 minus 1. Therefore, by the principle of mathematical induction, 9 to the n minus 1 is divisible by 8 for all n greater than or equal to 0. Or all integers n greater than or equal to 0, if you want to be very, very clear. But hopefully that is clear from the rest of the context of the proof. What do you think? Induction! We did it. And we are at the end of class. I have more induction examples. Maybe we'll do a couple more next time just to finish it off, since this does seem to be the sticking point with for a lot of folks. But hopefully it feels all right. Cool. See you next time. Have a great Wednesday.